So something important to take note of is what a conservative force is. Now, there's a difference between a conservative force and a non-conservative force. I'm not really going to get into the whole proof behind them. You can have a look at that in your textbook. We have what is a conservative force. So a conservative force is a force for which the work done is independent of the path taken. The important difference between conservative and non-conservative forces is whether it is dependent or independent of the path taken. So when we are dealing with a conservative force, it is independent of the path taken. And then a non-conservative force is dependent on the path taken. So an example of a conservative force would be gravitational force or weight, whichever you want to call it. And an example of a non-conservative force is applied force, frictional force, or tensional force. Okay. So how do we calculate the work done by a non-conservative force? So when we are calculating the work done by non-conservative force, this is the formula that we are going to use. So we have work done by a non-conservative force is equal to the change in mechanical energy. Now I'm going to separate both components and simplify them individually and then put them back into the formula. So the work done by a non-conservative force. Let's have a look at work net. Okay, so we know that work net was basically all of the forces or the work done by all of the forces that we were dealing with, right? So we had, in most cases, work done by applied force, work done by frictional force, work done by normal force, but let's leave out normal force in this particular case because it was always 0. So work done by Fg. So let's keep those 3 for now, okay? If there's a string or rope, there would be work done by tensional force. So let's have a look at these 3 for now. So this is work net, but we don't want work net. We want work done by non-conservative forces. So if we go back to our definition, non-conservative forces refer to applied force, frictional force, and tension, whereas gravitational force was a conservative force. So if we are calculating using non-conservative forces, we cannot use a conservative force in our formula. So we basically need to get rid of this. We need to remove work done by gravitational force. So we would then be left with work done by non-conservative forces is equal to the work done by the applied force plus the work done by frictional force. So that would be our work done by non-conservative forces part of our equation. Now, let us have a look at the change in mechanical energy. Now, we know that change refers to a final minus an initial, right? Or mechanical energy refers to the sum of your gravitational potential energy plus your kinetic energy. So because it's the change in mechanical energy, we are going to state that the change in mechanical energy is equal to the change in kinetic energy plus the change in gravitational potential energy. Now, we can also break up these kinetic energies and potential energies into more formulas, right? So we know that kinetic energy or change in kinetic energy refers to our final kinetic energy minus our initial kinetic energy. And our potential energy refers to the final potential energy minus the initial potential energy. All we've done so far is break it up according to the rule of change. Change refers to final minus initial. Now we can further break this up into each formula because, excuse me, because kinetic energy has its own formula and potential energy has its own formula. So let us break it up according to that. So we know that our kinetic energy has a formula of EK equal to a half mass times velocity squared. Now in this case, because we are dealing with final kinetic energy, we are going to use final velocity. And when we are dealing with initial kinetic energy, we are then going to use initial velocity. So let's expand this even further. So our change in mechanical energy will then be equal to a half mass times Vf squared minus a half mass times Vi squared. So that is just the kinetic energy component. Now let us have a look at the potential energy component. So we know potential energy refers to mass times gravitational acceleration times height. But because we are now dealing with the change in potential energy, we are going to have the final potential energy minus the initial potential energy. So when we are dealing with final potential energy, we will use the final height. And when we are dealing with initial potential energy, we will use the initial height. So that is then going to be mass times gravitational acceleration times the final height, because that is the final potential energy part. Minus, because remember this is still change, mass times gravity times the initial potential energy's height. Now, the student that has your mic unmuted. Sorry about that. Let us continue. So we've now broken up each final and initial component into its own individual formula, right? So from this point, you can see that if you look at the kinetic energy part, you can see that there's a common factor, a half m. The same way we did last week, if you remember when we were dealing with our work energy theorem last week, we dealt with how do we take out that common factor, right? Now we're going to do something similar today. In the kinetic energy part, we're going to take out a half m. And from our potential energy part, we are going to take out mg. Please give me a moment. Guys, if you want to have your own personal conversations, can you please keep yourself muted? I don't understand why you need to unmute yourself. So we all need to hear what you are discussing. If you're talking to someone at home or on the phone, that is your personal and private conversation. Keep it personal, keep it private. We don't need to hear what it is, okay? Okay, so from this part, like I mentioned earlier, all we are going to do is we are going to take out the common factors from each part. So let's start with our kinetic energy part. So from our kinetic energy part, we are going to take out a half m. and we will be left with VF squared minus VI squared. That is just our kinetic energy component. Now, if you look at the mechanical energy part of it, we can see that we have mg as our common factor. So that is what we are going to take out. And we'll be left with the change in height, or h final minus h initial. So that is all that we're going to do for the right-hand side of our equation. Pabalo, you have your hand up. Do you have a question?
Hi, sir.
Yes.
Sir, I don't know if it's only me, but I can't see the board.
Okay, students that are unable to see the board, can you put your, okay, let's do this. If you are able to see the whiteboard, can you put up can you indicate with a thumbs up? Okay, so it seems most students are. Pabalo, okay, let's do this. I will stop sharing and then start up the sharing feature again. Wait a few seconds. Let me know if you are able to see the whiteboard. Okay, so it is up again. Just wait a few moments. Sorry, not a few moments. Just wait a few seconds. If you are unable to see the whiteboard still, I suggest exiting the class. So click on the leave button, exit the class, and then re-enter the class the same way you originally did. Wait a few seconds. If it still does not show up, or if the whiteboard still does not appear, it could be a signal issue. So what I would then suggest is exit again on your cell phone or your laptop, whatever you're using. Go to the Wi-Fi options or the data options, whatever you're using, and turn the data or Wi-Fi off, and then on it again, and then connect. Hopefully that should resolve the issue. Okay, so I see there are a few chats. Let's just have a look at the chats. Will you just be covering the basics to work in energy power in this lesson? Priyanka, no, we won't be covering the basics. Remember, I'm just showing you how to get the formula. Because this is a different formula as opposed to the one we did last week. What we will do is, once we're done with the formula, we will move on to past paper questions. I think there's 3 past paper questions that are on the board that we will attempt. Grandmaster, you have your hand up. Do you have a question?
Oh, hello, sir.
Yes.
Yeah, so like we can see properly. Can you please like use a bright color or something? Because like we can see properly.
Okay, I will use. Are you able to see the white and the blue?
Nah.
So you can't see the white handwriting. Let me go up, then you can have a look at the white handwriting. Are you able to see the white?
Yeah, I can see it.
And the blue at the bottom?
Yeah, I can.
So it's just the orange and the red that you can't see.
Yeah, I can see it like properly, like yeah.
Okay, I will use the white and blue instead, okay?
That's cool. Thanks.
Okay. Okay, so let us continue. So now that we okay, just a quick thing before we continue. Are you guys able to see the green? If you are able to see the green, you can just indicate with a thumbs up. Okay, perfect. So I'll use the green instead of the red. Okay, so to continue from where we last left off. So we now simplified the left-hand side of our equation, whereby we broke up, or we simplified work done by non-conservative forces. We then simplified the right-hand side of our equation, whereby we simplified work done by, or not work done, sorry, where we simplified change in mechanical energy. So all you need to do is put those 2 components together, and you will be able to calculate work done by non-conservative forces. Now, something important to take note of when you're dealing with this section is that height is important. Height is your gravitational potential energy part. So when you're dealing with height, in order for you to differentiate between initial and final height, is you go back to where the object started. The starting point of that object is the initial height. The ending point of that object is the final height. Please do not confuse displacement with height. When you are dealing with vertical motion, then you will deal with displacement through a vertical plane that looks similar to height, but don't confuse the two, okay? For this case, we'll mostly be looking at past paper questions that involve an inclined height. So basically, all you'll need to do is look at the two endpoints of the triangle. One of those two will be your final height or your initial height, okay? So that is our formula. Let's have a look at some past paper questions. So I'm not really going to go through the definition. What I'm going to do is I'll just look at the calculation parts of it. The definitions are already up there in case you've forgotten. Okay, so this is from a 2018 November exam paper. So if you want to find out what exam paper the questions that I'm doing are from, all you need to do is look at the top right-hand corner of the exam paper. It'll show whether it's a prelim paper, a November paper, and the year. Okay, so our first question, we have the diagram below drawn to scale, not drawn to scale, shows a vehicle with a mass of 1,500 kgs. So that mass is important. Starting from rest at point A at the bottom of a rough inclined plane. So that is extremely important. Do you see it states starts from rest at the bottom of a rough inclined plane. So that second line, it's got three pieces of important information in one line. Starts from rest indicates initial velocity is 0. Starting at point A at the bottom of the rough inclined plane, at the bottom of the plane, that's your initial height. That means your initial height is point A, your final height is point B. And a rough incline, that means that there is friction because this thing is rough. So let's make a note of that. So this is our H initial, and V initial is 0 at this point. Then it states point B is 200 meters above the horizontal. So we now know that our final height is 200 meters above the ground. And our initial height would be 0 meters above the ground because it's on the ground. So we now know that our object has a mass of 1,500 kgs. The initial velocity is 0. The initial height is 0. And the final height is also, well, not also 0, but the final height is 200 meters. It then states the total work done by the force that moves the vehicle from point A to point B in 90 seconds. So we now have delta T, which is 90 seconds. We're now given time is 4.80 times 10 to the power 6 joules. So that is the work done by the applied force, or you can call it the work done by the engine, whatever you want to call it. as long as you understand that the work done by the force that moves this vehicle from point A to point B has a work of 4.8 times 10 to the power 6 joules. Please do not confuse this with a force. This is not a force of 4.8 times 10 to the power 6. This is a work. So don't substitute this value into force. This is the work itself. They have now given you the actual work value. Okay. So our first question is define a non-conservative force. It's on the right hand side. You can have a look at that. Our next question, is force F a conservative force? So they want to know, is the force that moves this vehicle from point A to point B a conservative force? Now, if we remember back to when we started our session, we stated that the examples of a conservative force, one of them was gravitational force. If we look at the force that moves this vehicle from point A to point B, that is not a gravitational force. That can be considered an applied force. Then we moved on to work done by non-conservative forces at the beginning of our class. And we stated a few examples of work done by non-conservative forces are applied force, tensional force, and frictional force. So if we have a look at this, this can be considered an applied force. So the answer to this question is no. This is not a conservative force. This is actually a non-conservative force. So the answer to 5.2 is no. This is a non-conservative force. So all you need to do is say no, or you can say no, it is a non-conservative force. Excuse me. Okay, so let us progress. Okay, let's just go back to 5.2 for a second. I would recommend that you learn the differences between conservative and non-conservative forces. They do sometimes ask you for examples, or they ask you, is this considered a conservative or non-conservative force, as is this case. Something else that's important is you cannot use work done by non-conservative forces formula if you do not know what a non-conservative force is. How are you going to substitute all the non-conservative forces into the formula if you do not know which forces are non-conservative forces? So I would recommend that you learn them. Work done by, applied force is a non-conservative force. Gravitational force is a conservative force. Tensional force is a non-conservative force. And frictional force is a non-conservative force. So I'll repeat that once more. All of our non-conservative forces are applied force, tensional force, frictional force. Our conservative forces are gravitational force, okay? And I would recommend learning that. The quiz that I'll release later in the group, there is a question on that. I think there's maybe 2 questions on that, if I'm not mistaken. Okay, so our next question is question 5.3. Calculate the average power generated by force F. So I know we have not yet covered power in our classes. It's something that we will do maybe at next week or the week after that. So I'll just quickly explain it now and give you the formula. So if you don't understand how power works, don't stress about it. We will get to it in our classes. This is just a past paper, so it encompasses all the topics, okay? So the formula for power, or average power, is P average is equal to work over change in time. Now keep in mind, because we are calculating the average power of force F or of the applied force. We are going to use the work done by the applied force. So if you are calculating power of a particular force, make sure that you use the work of that particular force, okay? So all we need to do is substitute the value of the work done by the applied force, and that is 4.80 times 10 to the power 6 all over our time. Here is our time, and that is 90 seconds. Make sure that your time is always in seconds, okay? From there, you can put this onto your calculator. Now, once you put this onto your calculator, you're going to get an extremely large value, okay? So you can either write that value as is, or you can convert that value into scientific notation. Whichever you feel better with doing, stick to that, okay? So that's going to be 53,333,33 watts. That W does not stand for work. That W stands for watts. W-A-T-T-S. Watts is the unit of measurement of power. The same way joules are the unit of measurement of work, watts are the unit of measurement of power. Okay. If you were to write this in scientific notation, this would then just be 5,33 times 10 to the power 4 watts. Okay. So just give me a moment to check if there are any questions in the chats. Okay, so it's clear, so everyone seems to be okay so far. Okay, so our next question, question 5.4. So the speed of the vehicle when it reaches point B is 25 meters per second. So that is now our final velocity, because we've stated that point B, which is the top of this incline, is our final. So the bottom, which is point A, is our initial. The top, which is point B, is our final. So we now have the initial velocity as 0, the initial height as 0, the mass of this object as 1,500, the final velocity as 25, the final height as 200, and we have the work done by the applied force as 4.8 times 10 to the power 6. So we have quite a few values that we can now use, okay? So question 5.4, calculate, or rather state, the work energy theorem in words. So the work energy theorem states that the work net done on an object is equal to the changing kinetic energy of that object. Okay, we've covered that in last week's class. Then question 5.5, we have use energy principles. So something important to take note of. Energy principles does not only refer to your work net equals changing kinetic energy formula. Energy principles refers to work net equals changing kinetic energy, work done by non-conservative forces equals change in mechanical energy, and it's also the initial mechanical energy equals the final mechanical energy. But you can only use the conservation of mechanical energy formula, which is initial mechanical energy equals final mechanical energy, if friction is 0. So if the system is frictionless, or if they state it is free from external forces, or if they state it is conserved, or if there's any indication that states that friction is 0, then you can use your initial mechanical energy equals final mechanical energy. So for this particular question, we can either use work done by work net equals change in kinetic energy formula, or we can use work NC equals change in mechanical energy. We cannot use our conservation of mechanical energy formula because there is friction present in the system, as the question initially stated, a rough incline. Okay. Because today's session is focused on work done by non-conservative forces, I'm not going to use the work net equals change in kinetic energy formula. I'm going to use the work done by non-conservative forces method. So let's start with our formula. Our formula is work done by non-conservative forces equals change in mechanical energy. Now, I don't want to use up a lot of space to break up this work done by, or rather, my mechanical energy component. So what I'm going to do is, instead of writing mechanical energy, I'm going to break up what mechanical energy is. So we know that mechanical energy is equal to change in EK plus change in EP. Whether you write it like this or you write it as change in EM for mechanical energy, you'll get the same mark. Keep in mind, you get 1 mark for formula, okay? So you can even start it off like this, it doesn't matter. So let's see. We know that there are 4 forces acting on the system. We have 4 forces in total. We have the applied force, we have frictional force, we have normal force, and we have gravitational force. Now, we're not going to look at normal force because it always results in 0. So we're basically just going to ignore that, okay? Because the work done by a normal force is always 0. Whether it's an incline or a horizontal plane, it's just always 0, so we can ignore it. I'm going to focus on the 3 forces that are involved, which is applied force, gravitational force, and frictional force. Now, from those 3 forces, which of those 3 forces are non-conservative forces? Because keep in mind, we cannot use a conservative force in a non-conservative force equation. So we know from applied force, frictional force, and gravitational force, only applied force and frictional force are non-conservative forces. We know that gravitational force is not a non-conservative force. So I'm going to exclude the work done by gravitational force. So when I break this up, I'm going to break it up into the work done by the applied force plus the work done by kinetic frictional force is equal to, now we previously broke this formula up when we first started today's class. We know that this is a half mass into VF squared minus VI squared plus mg H final minus H initial. Okay. So from this point, all we now need to do is substitute. But something important, I have not seen our kinetic friction value. Did they give us the force, or did they give us work done by kinetic friction? No, they did not. Did they give us the kinetic frictional force? No, they did not. So because we do not have the kinetic friction force, nor do we have the work done by kinetic friction. Before we even progress with this formula with question 5.5, let us stop and first calculate the force of kinetic friction. Let us first calculate our frictional force so that we can substitute that into our formula. Okay. So let's see. If we want to calculate, wait, just give me a moment. Oh, sorry, never mind. It's my error. I didn't read the question nicely. our goal is to actually calculate kinetic frictional force. Sorry about that. Sorry about that. We can't calculate it beforehand because the end point is to actually calculate it. So at the end, we need to calculate the work done by frictional force. So our final answer must be WFK equals something. Okay, so the whole goal of this question is to calculate the work done by kinetic friction. So let us start substituting. First, we need to substitute the work done by applied force. So if we go back to our question, it was stated in our question that the work done by applied force is 4.8 times 10 to the power 6 joules. So we substitute that in. And because we do not know, or not because we do not know, rather because our goal is to calculate the work done by our kinetic frictional force, we are now going to keep that as WFK. Yes, you have your hand up. Do you have a question?
Oh, hello, sir.
Yeah.
Can you please raise your voice because you're kind of too low?
I'm actually sick, so I'm not going to be able to raise it any further than I already have. What I would recommend is, are you using a cell phone?
Yes.
Okay, so do you see there's 5 options at the bottom of your screen? You've got that
Yes.
big red button to leave, you've got those 3 dots, and in the middle, you've got what looks like an audio button. Do you see that?
Yes.
Click on that audio button. You should see 3 options that pop up: device, speaker, and audio off. Do you see that?
Yes, I can see that.
Is yours on, is the tick next to device or next to speaker?
Next to device.
Okay, so click on speaker, you'll see it'll amplify the volume.
Okay, thank you.
Is it better now?
Yes.
Okay, so all the students that are unable to clearly hear me, I would recommend you do the same thing directly, well, not directly, but in the middle, there's 5 options at the bottom of your cell phone. Click on the audio option, click on speaker, you'll see it'll amplify my volume. Alternatively, you can use earphones. Yeah, so let us proceed. Okay, so basically what we've done so far is we've substituted the work done by the applied force, and we've brought down the work done by frictional force, because that is what we are trying to calculate. Next, we need to deal with the right-hand side of our equation. So we can bring down the half. Then we need to substitute the mass. So I believe the mass was 1,500 times the final velocity was 25. Don't forget, you need to square the velocities. So that'll be 25 squared minus the initial velocity was 0 squared plus mass. If you are not confident in your memory or your ability to remember important information, I would always recommend that you go back and forth between the question paper and your answer sheet and look at what each individual value is. If you substitute the wrong value in the wrong place, chances are you are going to get a wrong final answer. So always double check the values that you substitute, okay? Then our mass was 1,500. Gravitational acceleration is 9,8. And our final height, what was that? Our final height was 200 and our initial height was 0. So 200 minus 0. Now, what we can do is put the entire right-hand side of our equation into our calculator. So a half times 1,500 times 25 squared minus 0 squared plus 1,500 times 9.8 times 200 minus 0. Please be extremely careful on how you put certain things into your calculator. I've seen too many cases whereby people write the correct thing but don't know how to use a calculator, and then their final answers are incorrect. So make sure you practice putting in values on your calculator so you avoid errors that could have otherwise been avoided, or errors that will result in an incorrect wrong answer. I mean, why must you do all of this calculation, all of this hard work, just to make a silly error on your calculator, right? So make sure, even if you do put it into your calculator and you feel the answer is correct, clear your calculator, put it in a second time so you make sure you get the same value again, okay? And always make sure that your calculator's on decimal, okay? It must be on that capital D, okay? Okay, so from this point, we've now put this value into our calculator, and we now have 3,408,750, okay? And we've got work done by kinetic friction. Now, my work done by my applied force, I'm going to take that to the right side. So it's now going to become minus 4,8 times 10 to the power 6. Okay, so from this point, I can put the right-hand side on my calculator once again. So subtract 4.8 times 10 to the power 6. And you should get the work done by kinetic friction as negative 1, let me see, 1, 2, 3, 1, 2, 3. So negative 1,391,250 joules. Keep in mind, we're calculating work, so our answer must be represented in joules. You can also represent that in scientific notation if you want to. If you were to represent it in scientific notation, it would be work done by kinetic friction is equal to negative 1,39 times 10 to the power 6 joules. So it doesn't matter whether you leave it as negative 1 million and so on, or you represent it in scientific notation, you'll get the same marks or the same number of ticks irrespective, okay? So that is question 5.5. That is the entire work, energy, and power question from our 2018 November exam. So before we move on to 2019, does anyone have any questions relating to what we've done? Yeah. Okay, I see there are a few questions in the chats. Wouldn't the average power answer be in kilowatts? Okay, so the concept of kilowatts or watts, I would recommend you leave your answer in watts. I know when you I think it was in grade 11, you previously did the kilowatt hour and you came across average power and you left it in kilowatts, right? But for work, energy, and power, I would recommend you leave your answers in the SI units, okay? If you were to write your answer in kilowatts, you'd get the same marks as someone who wrote it in watts. So why must you waste time and convert it to kilowatts or to scientific notation when you're going to get the same amount of marks as the next person who didn't do that? So don't waste time, just write it as is and move on to the next question, okay? Remember, you've only got 3 hours to answer all of these questions, plus go back and check all of your answers. And when you're working with time, you're under pressure. So I would strongly urge you to just leave your answer in the SI unit, even if it's not in scientific notation. Just write your answer, put the unit of measurement, and move on. Okay.
Yeah, but sorry, the answer
Yes.
the average power answer you have isn't right for the watts. It's supposed to be 5,3. If you put in 5,33 times 10 to the power 4, it's giving you a different answer from the first one. I know you're trying to write it in scientific notation, but it's giving you a different answer.
Okay, just give me a second.
It would be 53.
1, 2, 3, 4. Yeah. Okay, you can write it like this: 53,33, and you can have it in times 10 to the power 3 watts, or you can have it as 5,3 sorry, 5,33 times 4. Was that your question?
Yeah, thanks. Thank you, sir.
So it doesn't matter which one you use. They're both scientific notation. The only difference between them is I chose to put my decimal after the 5. You can just as easily put your decimal after the 3. You could have even had 10 to the power 2 and put your decimal after a certain number of 3 digits. So I would recommend just leave your answer, stop at this step, and move on. Don't waste time to convert it to scientific notation. I only did that so that you can see what it would look like in scientific notation, but I would recommend just move on, write your answer, move on. Don't waste time. Okay. Okay, so just give me a moment. I saw there was a few more questions in the chat box. Okay, so is it possible to draw the free body diagram on the side so that we can know which forces act on the object? Okay, just give me a moment. I will draw the free body diagram. Okay, so if our object is on the incline, right, I would suggest drawing your incline as well. So this dot would represent your object. Then your incline be represented by that. We don't know the value or the angle of the incline, so you can just leave it out. Now, the forces that are acting, we know that there's an applied force that is moving the vehicle from point A to point B. We know that because this vehicle is on a surface, there's going to be a normal force. And normal force acts perpendicular to your surface. I know that I use a lowercase n when I use normal force or when I represent normal force. That's just my personal preference. You can use a capital N, you can use FN. It's up to you. It doesn't really matter. Okay. Then in addition, there is a kinetic frictional force, and we also have weight, or FG, whichever you want to call it, that is acting vertically down. Okay, so that would be our free body diagram. If you want to include your displacement, because the object is going up the incline, your displacement would also go up the incline. So that would be the free body diagram should you wish to draw it. But this question didn't really require us to draw it. So yeah, as long as you know what forces are acting on you, or once you figure out what forces are acting on the object, your next step is to eliminate the conservative forces so that you have the non-conservative forces left, okay? Okay, so I'll ask once again quickly before we move on. Does anyone have any questions relating to what we've just done with calculating non-conservative forces before we move on? Okay, so let us move on then. Okay. So we've got 2019. Let's see if we can just squeeze both of these in before we end. Okay, so this question paper is from a 2019 exam. We've got an object of mass 1.8 kgs, so that is important, the mass of the object. Slides down a rough curved track. So rough, that indicates kinetic friction because the object is moving. Keep in mind, if the object is stationary, it's static friction. If the object is moving, it's kinetic friction, okay? But when you're dealing with work, energy, and power, in most cases, the object is moving through a displacement, so it's going to be kinetic friction. So an object of mass 1.8 kgs slides down a rough curved track and passes point A. So because it's sliding down the track, we know that it's going to end at either B or C. So depending on where it ends, either B or C, that would be our final points, okay? So we would assume A to be our initial point for this particular setup, which is 1.5 meters above the ground at a speed of 0.9 meters per second. So that velocity is important, that height is important. The object reaches point B at the bottom of the track at a speed of 4 meters per second. So because they've stated point B as the final, so this is going to be our initial height, which is 1.5 meters. This is going to be our final velocity. Sorry, I mean the initial velocity, which is 0.95 meters per second. My final velocity would be here at point B, and the final height would be 0 meters above the ground because it is on the ground. Okay. The first question is a definition question. It's on the right-hand side if you want to have a look. Question 5.2, name the conservative force acting on the object. So this is the second question paper in a row that they've made reference to either a conservative or non-conservative force. So as you can see, it's quite important to know the examples and the definitions of both a conservative and a non-conservative force. So our examples of a non-conservative force: applied force, frictional force, tensional force. Examples of a conservative force are gravitational force, Fg, or if you want to call it weight. So our question 5.2 stated, name the conservative force acting on the object. So that is gravitational force. Okay. Next we have question 5.3. Is mechanical energy conserved as the object slides from point A to point B? So like I previously mentioned, mechanical energy is only conserved in a system that is free from external forces, or in a system whereby frictional force is 0. So in line 1, they've made reference to slide down a rough curved track. The usage of the word rough indicates friction. So because they've indicated friction, we therefore know that this system is not isolated, so we can therefore not use our conservation of mechanical energy formula, right? So our answer is no. The mechanical energy of the system is not conserved, which means that the initial mechanical energy of the system is not equal to the final mechanical energy because frictional force is present. So they said give a reason to your answer. So you'd get 1 mark for stating no, and your second mark would be to state frictional force is present. Okay, so that would give us our 2 marks. So always remember that whenever frictional force is present in a system, mechanical energy is not conserved. Therefore, in that particular question, you cannot use the conservation of mechanical energy formula. Okay, it is only in systems whereby the system is conserved or frictional force is not present can you use conservation of mechanical energy formulas. So let us proceed. We have question 5.4 that states, calculate the gravitational potential energy of the object when it was at point A. So we now need to calculate EP at point A. That is question 5.4. So we need to calculate the gravitational potential energy at point A, which is also the gravitational potential energy or the final gravitational potential energy. You do not need to include EPA equals EP final. I'm just showing that as an indication that you can use either notation, it doesn't matter. And as a reminder that that is the final potential energy, because if you look at question 5.5, we are most likely going to calculate work done by non-conservative forces because it's got 4 marks in it. So it looks like there's might be, and you can also see using energy principles. So that's why I am representing it like that, so we can directly substitute this value into 5.5, okay? But you could have just represented it as EPA or EPF, it doesn't matter, okay? You could have even just said EP, doesn't matter. Whatever you choose to represent it as, it's fine. Okay, so we know that that is mass times gravity times height at point A, or you can say HF. So that is then going to be equal to the mass, which is 1.8 kgs times your gravitational acceleration of 9,8 times your final height. Your initial height. And one more important thing that I've just now noticed is that that is not final, that is actually initial. Sorry about that. A is your initial potential energy, not your final potential energy. Sorry about that. Okay, so we will use initial height, which is the height at point A. So that is 1.5 meters above the ground. And if we put that into our calculator, 1.8 times 9.8 times 1.5, that is then going to give us 26,46 joules. Keep in mind, we're calculating energy. Energy is calculated in joules, okay? So work, which is a form of energy, kinetic energy, mechanical energy, gravitational potential energy, those are all calculated in joules. Okay. So that is the gravitational potential energy at point A. So our next question, question 5.5. Using energy principles, calculate the work done by friction on the object as it slides from point A to point B. So if you notice, the paper that we did previously, 2018 and this 2019 paper, they're almost identical. Previously we calculated work done by frictional force. Once again, we're calculating work done by frictional force. Previously, they asked for the conservative force definition. We had to do that once again. They previously asked for an example of a non-conservative force. Now we did a an example of a conservative force. So your question papers, if you go through a few question papers, they are almost identical each year. All they do is slightly change the diagrams or slightly change the values. So if you can go through all your past papers, practice them, even if you did the paper already, do it a second time, a third time, a fourth time, continuously repeat the same paper if you have to. Even though you already know the answer, you might even know the answer that you're going to calculate by just looking at the question if you've already done that paper like 5 times already. The goal is not to know the answer. Answers are easy. The whole point of this is to know the process of how to obtain an answer. The point of repetition that I recommend you use in math and physics is to be able to build that process into your memory, whereby you don't even need to think that much. You already know the process. Before your brain even thinks, your hand is already writing down the steps because you already know the process. So the process is more important than getting an answer. Okay. So question 5.5. Using energy principles, calculate the work done by friction on the object as it slides from point A to point B. So we're going to use the same formula as we did previously. Okay, but for this particular formula, I'm going to change the potential energy. Instead of representing it as its most simplified factorized form, I'm going to represent it as the final potential energy minus the initial potential energy, because I already have the initial potential energy and I just want to substitute that value. I don't want to have to recalculate it, okay? So this would then be, okay, so for this left-hand side, we need to go back, see what forces are acting here. So we have normal force, applied force, gravitational force, and frictional force. We're going to ignore normal force because the work done by normal force is always 0. So we now have applied force. Well, technically, we actually do not have applied force, because they stated slides down. They didn't say it's pushed down. They didn't say a force is applied to it. They said slides down. Because they made use of the word slides down, we then know that there is no applied force in this particular example. So if you were to draw a free body diagram of this, it would look like this. So you incline, you'd have displacement down the slope, you'd have frictional force up the slope, you'd have normal force perpendicular to the slope, and you'll have Fg vertically down. So as you can see, there's no applied force that is pushing this object down the slope. The reason that the object slides down the slope is due to the component of Fg. That's the force that makes the object slide down, and that is not an applied force. That is a component of Fg. Keep in mind, we do not use the components of Fg when we are using work done by normal force. The reason is that, keep in mind, Fg is a conservative force, and components of Fg are still Fg technically. So because Fg itself is a conservative force, the components of Fg are also conservative forces. Therefore, we cannot use them in non-conservative force calculations. So we need to figure out what forces are acting on this object. It's applied force. Sorry, I keep on saying applied force. Sorry. There's no applied force acting here. It's frictional force and gravitational force. So because we only have 2 forces that are not work equals to 0 forces, because we're ignoring normal force, so the only 2 forces that we are going to look at is our Fg force and our friction force. So between Fg and friction, which are non-conservative forces? We know that Fg is a conservative force, therefore the only non-conservative force acting on this object is Fk. So we do not have applied force, therefore we are just going to break up work done by non-conservative forces into the only non-conservative force that is acting on this object, which is Fk. Then on the right hand side, I'm going to break this up into its formula, which is a half mass into Vf squared minus Vi squared plus, I'm going to make this Ep final minus Ep initial. Keep in mind that we already calculated Ep initial. So because we are calculating work done by kinetic friction, I'm going to bring that down, then substitute my mass, which is, let's see, 1.8. So substitute a mass of 1,8 into velocity. Let's see, what's the final velocity? Our final velocity is 4 meters per second. Our initial velocity is 0.95. So this is going to be 4 squared minus 0.95 squared plus. Now, my final potential energy can be broken up into the formula mass times gravity times H final. Okay, so let's just quickly sub that in. So this is going to be mass, which is 1,8 times gravity, which is 9,8 times H final, which was 0, because at point B, which is our final in this case, our object is on the ground, therefore the height above the ground is 0, and that is minus 26,46 joules, which we calculated in question 5.4. Now, all we need to do from this point is put the entire right-hand side our calculator. And that then gives us negative 12.87. So the work done by kinetic friction is negative 12.87 joules. Something important to take note of is, as you've seen in the previous question and in this question, our work done by kinetic friction is always a negative value because it is a force that removes energy from our system. Okay, so if you ever end up with a positive work done by kinetic friction value, please go back to your calculations and see maybe you made an error somewhere. Okay, so before I move on to the next question, let's quickly check the chats. Okay, so everyone seems to be okay. Let us proceed. Now we have question 5.6. Surface BC in the diagram above is frictionless. This is very important because they've stated that BC is frictionless. It now means that mechanical energy is conserved between BC. So we can now use our mechanical energy formula. So 5.6, what is the value of the net work done on the object as it slides from point B to point C? So we need to now figure out what the net work done on this object is equal to. So let's see. They've stated that because this object or because this surface is frictionless, right? We're not even going to use our mechanical energy formula. It's only one mark, which means that your answer is simple, right? So between B to C, let me draw a free body diagram. So if this is our object, because our object is on a flat horizontal surface, you've got normal force and gravitational force that are linear to one another. Then you have kinetic friction as per the old diagram, right? That's what we previously had if the old diagram was on a flat surface. But then they stated that the object or the surface is frictionless. So we would therefore remove kinetic friction because it's frictionless. So if we were to calculate work net, we would calculate the work done by normal force plus the work done by Fg. And we know that because displacement is moving from B to C, it's moving in the left direction, displacement will be moving in the left direction, right? Our angles would be 90 degrees for both. And a 90-degree angle, cos of 90, would result in 0. So because it's a flat horizontal surface, normal work done by normal force will be 0. Work done by gravitational force will be 0. There is no applied force and frictional force has been removed. Therefore, you will end up with a work net of 0. The last question, we need to calculate work net, right? For BC. So if we need to calculate work net for BC, give me a moment. So if we were to calculate work net between points B to C, keep in mind that BC was stated as a frictionless surface, okay? So this is between BC only. So we would then have the work done by normal force plus the work done by Fg. Because keep in mind, BC looked like this. This is our object. It was moving to the left, so that's displacement. We had normal force and we had Fg. There was no frictional force. It stated that BC is frictionless. Per, you have your hand up. Do you have a question?
Yes. So when calculating the friction there, do you use other forces acting there or do you use only friction?
Okay, it depends which method you want to take. So there's two methods that you can use to calculate question 5.5. The first method is the one that we did last week, whereby you can calculate using work net equals change in kinetic energy. If you were to use work net equals change in kinetic energy, the forces that you would use are frictional force and gravitational force, okay? Because work net refers to all of the forces, irrespective of whether they are non-conservative or conservative. If you want to use the method that we've used today, whereby we calculated using work done by non-conservative forces, you can only calculate the work done by non-conservative forces in this method. You do not include work done by conservative forces. We know that gravity is a conservative force, therefore we will exclude work done by gravity. The only forces that we take into consideration are work done by frictional force, because that is a non-conservative force, and we do not have applied force in this particular question. If there was applied force, we would have said work done by applied force plus work done by frictional force. Does it make sense?
Yes.
Okay. Okay, then
please send the summary of this topic on the group.
yes, I will do that. I will give you the last question as homework to do. If you get stuck with it, you can send a message in the group